just recap what we have done last 4 lectures. So we talked about the supervised and unsupervised learning, sort of like in the basic mode. So or for individual tasks, we introduced one of the most widely used and classical methods from supervised learning, like a regression and classification, and unsupervised learning on the density estimation and dimension reduction. So from this lecture onwards, we will start to dive into deeper like methods, but we will still be like anchoring ourselves on the few like methods, also on the supervised tasks and unsupervised tasks. So this lecture and next lecture, we will be talking about neural network. So we will starting with supervised tasks for this lecture, and then unsupervised tasks for next lecture. And then after that, we will talk about the Gaussian process, like again, like tackling the supervised tasks. Yeah, so once you know sort of what we are tackling in these like courses, like it will just be like repeated, but just with the different like methods, but also like a different breadth and depth in terms of the methods. So today is more about the neural network. I'm always like a bit hesitant to teach a neural network like 101, because it's very easy to give people the impression that, wow, you know, that's what all the hype is about. It's just like few neurons and string together and just like stir the pot and things happens. That's sort of it's not the impression that I hope I am giving today. Of course, the study of, like, when we talk about like deep learning today, like most people are talking about the neural network, and we think about all the machine learning hypes is all about the neural network. So the field itself is very broad, and there are lots of theoretical depth of that field. So we give you some of the exciting like research that people are doing. But of course, like we need to start somewhere. So today will be very basic, but also more like on the practical front. But it's also like important to just keep in mind that like whatever we talk about today is not even like scratching the surface of what is in the study of deep learning. So the basic concept, as we will see today, is like once we understand some of the classical methods, then we can start to talk about the limitation of those methods, and naturally, like a solution of that will be the neural network. So we've also talked about some of the concepts that we have learned, say, in linear regression and in the new form, right? So in the neural network, there's something called weight decay, which is the same form of a regularization, as we have seen in the first 2 lectures. We also have touched upon in the logistic regression on a gradient descent, and this will come back in the neural network again. But the big bulk of the things I want to like explain today is auto differentiation and back propagation. So as you will see, this form the basis of a neural network and why it become like popular now. Yep, so let's get started. So let's start by talking about the limitation of the classical methods. So we have seen the linear regression and logistic regression. So just to recap, so in this case, what we try to do is to say we will assume in the supervised task, the output y depend linearly with x, meaning that I will do like the w dot x. In principle, I do not need to just use x, so I can have any input feature x, but I will try to turn that into a more expressive features, phi of x. And hopefully, like in phi of x, the label will be linearly the dependence on the input like phi of x. And that is for the regression task. And we will talk about, you know, if you go to the classification task, you have this like tapering function. The sigmoid like function come naturally because of the log of odds. And the nice thing about the linear regression, as we have seen, is everything is purely analytic, right? From the maximum likelihood solution to the regularized solution, like the posterior and also the predictive distribution And this is the nice thing, because like this is like when you do the optimization, it's also like convex and everything is super nice. For the classification, it's slightly more complex, but since the sigmoid function is just a monotonic function, so the gradient descent will also work quite quickly. Hopefully, you have seen that in your assignment. But there is a problem with this assumption, right? This is a very strong assumption because we predefine the features phi of x. And arbitrarily, it's very hard to come up with a phi of x that will fit the output in the form of like wu dot phi of x. And this is what the neural network want to solve, which is to say, well, like why not, instead of just using this very restrictive explicit form, why not we just consider the feature like itself is a learnable function, so some parameters. And conceptually, it seems like this is something quite straightforward because we know most of this is just some optimization. Of course, if I parameterize this, I can also just run a gradient, a descent. But this actually like does not speak much. Like it really just say that we will find a function, right? That are parameterized in some way. There is reason why, as we will see, the idea of a neural network is not new. Like it did not come in 2010. It came in like 1960, right? So the idea that linear regression is too restrictive, people have seen sort of the machine learning. I will change that. But like people have seen like the possibility to improve on that, but the neural network has largely stymied for many years because the story is that some big shot in the field in machine learning thinks that it would not work. So people actively discourage people to work on that. And there are kind of intuitive reason why people think like that would not work. Because if I just randomly write down some function, I would expect the likelihood to be extremely non-convex. And even if I find a gradient descent, what is the chances that I will find a solution, right? So if you think about if I write down some really weird function, it shouldn't work. It turns out that some people like persisted. I'm not sure if they have really the theoretical like insights. They could have, but many of that it just turned out to be a magic that happens, and people started to understand why those like magic could happen, as we will see. But the upshot is, like do not always just listen to the big shot in the field say, like this field is not like promising. If you feel strongly about that, you should persist. So what is the idea? The simplest form of a neural network is what we call the multi-layer perceptron. So like we will talk about what it means by a perceptron, but the multi-layer part, like it just means that if I want to make a very complex function, then one obvious way is to say I will string together many simple function in a recursive way. And the idea here is that the recursive composition of simple function can make a very complex function. So if this seems a bit high level, you can think about the following. So let's say I start with a very simple sigmoid function, and I just allow the function to do like shifting, stretching, and scaling. You might think like this is such a simple function. What can it do? It turns out that you can do a lot. So for example, if I have a target function here in the dotted line, it turns out that I can just use a sum of all the different sigmoid function as shown in the dashed line here. Summing them up will give you the white line, which will be a good approximation of the dotted line. So you can imagine even starting with a simple function, if I use some recursive composition of nonlinear function, I can come up with a very complex function. So that's sort of the logic behind neural network. So mathematically speaking, for one layer, So here it's just saying that, for individual input X, I will like allow that to shift and scratch, and then I'll apply some nonlinear function F. F here can be the sigmoid function. This itself is not that expressive, but if I make something more expressive, so I can take some X, do some linear stretching and shifting. So remember, the W here also include the bias term. Like if you look at this as the WX plus B, so this has the stretching and also the shifting parts. And then I take a sigmoid function, and then I sum up all the sigmoid function with some arbitrary weights. So if I look at just the inner part here, up to the summation, this is kind of exactly what we just described, right? So I take some sigmoid function and then sum them up to make a new function. Of course, I can keep doing that to make it even more expressive. So I can take the sigmoid and then take the sum and so forth. So that's the simple idea. Or we call that the multi-layer perceptron. Somewhat a misnomer because most of the time we no longer use the perceptron function. We will see what that is. This very simple network 101 is classically known as what is the feed-forward network or fully connected network, meaning that given any input, I do some scaling and scratching, sum them up, further use that as a function, do some scaling and scratching, and sum them up. So, of course, this can be generalized to another a simple network that is not a fully connected network, but rather what we call a feed-forward network, meaning that I have some very complex network that I will just string together a different summation of the different part of the function. So, of course, there's nothing to stop you to do that. So this is still a functional form, just like your polynomial that you can optimize over gradient descent. Nonetheless, as I mentioned, in the beginning, back in the 1970s and 80s, very few people believe this could work. One is that this calculation can be quite expensive, even doing a simple gradient descent. But also, what is the chances that the likelihood with respect to the W is very smooth, so that you can find a solution? People say that it would be extremely jagged, just like if I fit a high order degree of a polynomial. It does not seem that it would work. It seems like it would just overfit the data. There are lots of magics that happens, we'll talk later. But this is why people are quite skeptical. But nonetheless, there are lots of tricks, even in this simplest network. There are lots of tricks that people have discovered, which we will not talk about in this lecture, but I want to give you some overview of some of the tricks. One is people have designed skip a connection, meaning that you do not go from first layer to the second layer to the third layer. You can do first layer to the third layer. And that is because most of the optimization is done by gradient descent. But for a very deep network, you will expect there's a problem of what we call the gradient to diminish. So let's say I want to calculate the gradient of the output with respect to the first layer. I will do some chain rule, as we will see later. But let's say each individual gradient is 0.1, right? So if I go to the next layer, it will be 0.1 square, so become 0.01. If I take the third layer, become 0.01, 0.1 cube, so 0.001. So the gradient with respect to the parameters will tend to have this exponential, the diminishing of problems. So in practice, it just means that if I update the weight based on the gradient descent, I might find myself to update some of the layer quite quickly, but some of the layer I never get to update because the gradient is too small. So skip connection have these nice properties to circumvent that. As we also see more, it turns out that even for this very simple network, and most things that people in astronomy just think, these are just some black box, turn out to be extremely profound. People found that even you train these very simple networks, you tend to find a solution that is sparse, meaning that it has a way to self-regularize. like just in your polynomial, if I use a very high order of a polynomial, I might tend to overfit. So sometimes you need to explicitly say, I want to do some regularization on the weights, as we have seen in this first lecture. But for different things in neural network, it seems to be able to train itself to a certain point where the solution becomes sparse. And in physics or mathematics, we always assume the rules of parsimony, or what we call Occam eraser. So for things like for a simpler solution, if I can find that, it tends to have a better way to generalize. And this is also something that people found. Like we come back to this point for some of the active research that is going on, but that seems to have these magical properties. The only thing that you need to ensure in order to do the gradient descent is that there is no circular loops. So you have a feed-forward models, meaning that you always go in forward from the input to output layers. I think like around 2017 and 18, people are quite into doing what we call NASH, the network architecture search. So not only we optimize for the parameters, we also optimize for the structure. So there are some tricks to find the optimal structure, but this turned out to be slightly not as popular now, partly because they are more powerful architecture like transformer or the other things that come out. They tend to be more general and require less searching on the methods. But these are just like one slide about some of the auxiliary thing that you want to keep in mind. The key things about let's go back to the basics. So as we have shown in the animation, the key thing here is that despite you are having a very simple network, you can mathematically prove, which we will not, show that even you have a two-layer like MLP, just like summing up a sigmoid and then doing a sigmoid, that itself can approximate any continuous function to arbitrary accuracy, which is not too hard to believe, right? If I sum up more and more sigmoid function, at some point I will be able to approximate that function. To prove this is actually not too hard, but require some notation that we have not learned in this classroom. So for example, how do you define a continuous function? A digression for people who have taken math courses, if you take real analysis, then you have quite a lot of theorem that are in this flavor. So a famous one is called the Stone-Weierstrass theorem. I think that's sort of the 101 theorem that you will learn in real analysis, saying that any continuous function can be approximated arbitrarily accurate with trigonometry functions. And in physics, you can also know that for any continuous function, if I keep expanding the Fourier series, I will be able to approximate that function very well. This is just saying that neural network in principle is a good idea, because any continuous function, including your consciousness, can be in principle approximated by only two layers of neuron, as long as your consciousness thought is a continuous thought, right? But this actually have a lot of problems. This statement really tell you nothing, because it does not tell you that you can easily find the solution. It just says that the solution could exist, is somewhere in this very high dimensional space. If you want to learn more insights why just stringing different small neuron can lead to very complex function, there are quite a few good playground. Like the TensorFlow have one, PyTorch has one. So it is something that you can play with that to see why just putting in simple function can somehow make very complex function. Okay, so why the name of multi-layer perceptron? The perceptron function it actually means a step function. So it actually means, I have some threshold, and beyond that is 1, and less than that is -1. And this is what people try to use in the 1960s. Why? If you have seen the imitation game, you have only a switch, on and off, based on some threshold. And people try to use that to mimic some of the decision based on the switching, like by changing the threshold A for the different nodes. You can see that this actually first proposed by Frank Rosenblatt. I do not know how to pronounce, in 1958. So this is absolutely not a new idea. The modern day that we use are usually not using such a step function for good reasons, because most of the optimization is done by gradient descent. And for gradient descent, you want to have the gradient. So if you have a step function, then you have a sharp kink in the function, which makes the gradient not smooth. So most of the thing we are not using the perceptron function, but for most cases, the name like MLP still sticks. So even you're using like a fully connected network, then most people will call them just the MLP. But to be more accurate, you can say like feed-forward network or fully connected network. So the objective here is really, really simple. So if you have understood what we have learned in the first 4 lectures, then they are the same thing. First of all, if I want to do the regression, I just want to minimizes the chi-square, right? So like just that now this function y have a more flexible form. Like previously, this y is just like w dot phi of x, but now it can be the summation of w dot phi of x summation of that. So you have a more expressive function that is parameterized by the w. And just to remind you that like this thing, of course, has some Bayesian interpretation. So you can look at this as the maximum likelihood with a uniform prior. And of course, if you do the classification, then the neural network should output y, and then the y will be used to calculate the loss entropy. But if you have a binary classification, so you want y to be 0 and 1. So meaning that each time you output y, you also want to first subject that to a sigmoid function. So make sure that it's the taper at 0 and 1. For the multi-class classification, exactly the same. It's just that now we are extending the simple linear model, which is phi of x dot w to y of k, with one catch, because if you do a multi-class classification, like you want the y to be the probability. So you want that to sum up to 1. So in the binary case, you can subject that to a sigmoid function, but for a multi-class classification, you will subject that to a softmax function, which we have also seen in the logistic regression. So you, like if you forgot, it just means that I will subject my temporary output y prime to the exponential of y prime divided by the sum of the exponential. Right. So the loss function will be this term. We also talk about how this can come just by looking at the likelihood in the Bayesian frame. Of course, there are lots of hyperparameters, right? So just like in the linear regression, we can predefine phi, but here you are having some generic recursive operation. So the number of hidden layer, how deep you want to go, or number of hidden nodes, they are all hyper parameters. One thing that is really interesting that people stumble on, and also why people think would not work, is people always think like neural network is high level polynomial, which is I'm always super offended when people say neural network is just a very flexible function. That's really furthest from the truth, because if it's just a very flexible function, it would not work. Just like a polynomial, if I have 5 data points, if I fit 100 order polynomial, I will just overfit. Somehow, the neural network does not. So you can have 1 million data points, you can fit 1 billion parameters, and it simply does not overfit. We will come back to that point why I think we started to have a really good understanding of why that is the case. Of course, I will not be able to explain that in all details, but this is the point that is important to keep in mind. It's really not just a flexible function. It is a flexible function, but have a lot of nice properties. By chance, a lot of them, I don't think people who persisted for 40 years, know that that could happen, but they think like, there might be a path forward, right? So just like the neural network, just like in the linear regression, you can always like prune the weights by regularization. So we talk about this in the linear regression. You can add this term, and this term can be like regarded as the prior term of the weight. So you have a prior belief that most of your weight should be 0, and you try to say, if I use a weight, it better do something. So, or put it simply, like this is sort of the inherent, what we call inductive biases of the rules of parsimony. So I hope that the solution to be as simple as possible. In most of the deep learning packages, including the PyTorch that we will play with like a little bit, there's something called weight decay. So weight decay is just gradually like turning up like lambda, meaning that I will let it find a solution first, but slowly I will increase the penalty so that it will start to encourage to find a simpler solution, yet will be able to describe the data. Right. By the way, I have like 2 very long like tutorial, as you have seen, for the neural network, so that will give you all the basic thing that you need to do that. I'm not sure how much I can get into the tutorial today. Like, we'll play with that a little bit, but it's important that you actually play with the tutorial. I think that is the most important part. Here it just like give you some overview and to dispel some of the misconception about like neural network as just a very flexible function. I don't know, like people love to say that without like knowing what is a neural network. That's really quite wrong. For neural network, one nice thing is that it tend to not overfit too much. But nonetheless, if you have finite like computing time, as we will see like later, if you have infinite like computing time, you always find the very nice solution after you train like long enough. But nonetheless, like most of us have no infinite time, and sometimes you will tend to overfit because you are still using a lot of parameters to fit a very small number of data set. So a practical way to do that is to do the early stopping, just like in the linear regression, like fitting a polynomial. You will just look at the training loss as a function of the number of steps that you trained. After you reach some point where you see the validation loss, let's start to get worse, then like you can do the early stopping and choose the best weights. Technically, right, as we discussed in the first lecture, you want to separate the training, the validation, and the test set, because you want the test set have nothing to do with any of your decision. But here the validation is deciding where to truncate, even though the weights like itself will never see the validation set, but that still helps to make the decision. So technically, you might want to have a test set, but in practice, it's probably not a big deal. So you can just use the training and the test loss and use the test set to set where to truncate. So how to optimize a very complex function? Of course, just like stochastic gradient descent, as we have learned in the logistic regression. So there's a 101 thing that they would think of. To think of this is not hard. The magical thing is that it works. I think that's all the surprises, right? So the goal here is that I have some parametric function that is seemingly very complex, but nonetheless is still a parametric models that depend on some parameters, the W. And my goal here is to find the best the W that minimizes the loss. And the way that we can do that is by doing the stochastic gradient descent. And just to remind you, what is the stochasticity here? Meaning that we take a sub-batch of the training data. Why that is good? Because even the space itself is not very jagged, that you still want to inject some randomness to your gradient descent, so it does not get stuck into some minimum point. Of course, to calculate the gradient descent, you need to calculate the gradient, right? So the question is, if you have a very complex function, how do you calculate the gradient? That's sort of the main core of the remaining time here to talk about how do you find the gradient. In principle, like finding the gradient is not hard. So you have learned from your high school, I can have a very complex function, f composite with g composite with h. If I just want to take the derivation, I would just do df dg, dg dh, dh dx, right? It's always a chain rule. So there are a few ways to do like gradients in your computer. The first one that you can think of is doing a finite differences, right? So if I want to study df dx, I can study delta f divided by delta x with some finite delta. That's not good. First of all, you need to calculate that like many times for different x's. And you also know that, there's no arbitrary way to calculate to know the delta x. So you take too small, like you might run into some numerical problem. If you take too large, then like it might not be a good approximation of the gradients. So that is fine, but not what we want to do. The other thing that you might have learned in your high school or some, I'm not sure there is a differentiation competition, probably not. So because that would be too dumb. So there are some integration and competition, but there are still some symbolic like a computation, right? So if I have a somewhat complex function, this is what like Wolfram Alpha do. So if you go to like Mathematica, you can have some tricks to say, even for a very complex function, I can still find df or dx in the symbolic form. But that is also not very useful in a way, because first of all, we do not really care about the exact symbolic representation of the differentiation. Like we just want the gradient to calculate how I descend the parameters. And like many of that, like if you write down of that, it's just like it's hard to express. It's super long, like, and who cares, right? So the only thing that is really like important for most of the cases is auto differentiation. So we will talk about what is auto like differentiation. So the idea here is that for any function, it really comes down to, as a human brain, we'll always just write down as some composite of some primitive function. You never come up with a function that you cannot write it down in some composite simple function, like exponential, log, sine, cosine, plus or minus, taking square, right? This is always operation that we do. And individual of them, the derivative is known, right? So 1 over log, the d log dx is 1 over x. X squared is 2x. This, for individual primitive like operation, the calculation is known. And if I just see all of this function as the composite of simple function, then it's just a long string of function is compositing each other, but then it's just a chain rule. So I want to use a chain rule to iteratively calculate the differentiation. This is very good for two ways. One is very accurate. This is by default, this is like the most accurate thing you can do, because you are calculating the analytic composite, the analytic like gradient for individual points. As we'll see, that it can also be quite efficient. And this is where the backprops like comes in. The downside, you do not have the symbolic form. You are just like storing in your computer the gradients of individual points. You have some numerical like value of what that gradient is, but who cares? Because this is exactly what we want. Because when we do the gradient descent, I want to take the eta times the nabla EW, right? So that is a numerical form that we want to do the SGD. So to make this clearer, so this is a specific example. So this is like one layer like MLP. So if I look at some output Y, and I want to estimate this with a one layer like MLP. So it will be some nonlinear some linear function, like Wx plus b, and then use a nonlinear function. And this function itself, this whole thing, the loss, can be decomposed into this string of operation, right? So I just say, I start with some x, I start with some the W, and then I will do a matrix multiplication to get to this point. So the add here is not your GNL, but rather the matrix multiplication. And then I will put this summing up with B, like get to this stage, take the sigmoid function, and I get to this part. And then here I do Y minus this part, take the square. So all these individual parts are primitive operation. So now if I further like define the individual outcome to be Y, Z, and H, If I want to update my W, I will need to calculate DL DW, right? But the DL DW can be written as DL DH, DH DZ, DZ DY, DY DW. So what you need to do is to calculate this string of things. So, but you still need two ingredients. One is that you need to know how to do the differentiation for individual steps. And that is trivial because we have decomposed that to all the primitive operation. The other thing that's more tricky is, of course, you know that when you calculate a numerical gradient, you are evaluating at certain point. If I do DL DW, I am doing DL DW at the current W. But if I want to decompose this into all these simple operation, then it means that I need to calculate what is the intermediate value. Because when I do DLDH, I need to evaluate it at H0. While what is H0 is at the particular input. So a particular input, say the W0, will give you a particular value of Y0, a particular value of Z0, and a particular value of H0. So when I calculate that by chain rule, individual block is evaluated at the exact evaluation of the function at a given point. Is that clear? So I think that is important. Knowing these two ingredients, it just means that you need to do two things. One is to calculate all the intermediate value, right? So given W, what is Y0, Z0, and H0. So this is called the forward passing. So you will just evaluate the function once. And once you have done that, then you can do what we call the backward propagation, meaning that I will first calculate DLDH, evaluate it at H0, use this one to calculate this block, evaluate it at Z0, and go back, right? So you might say, well, if I write this form, why do I have to do that in back propagation? Why not just do forward propagation? It seems like I can do the matrix multiplication also in the forward direction. So the amazing thing about back propagation is that it serves two purposes. One is that it's computationally effective because, let's say I want to calculate DLDB, because not only I want to update DLDW, I might also want to update DLDB. But DLDB in the gradient form will also reuse exactly this block, which I would have calculated from DLDW. So when I do the backward propagation, I am collecting the gradient bit by bit without repeating the operation. So I just calculate which part I need and then pass that to the part that we need. So by the way, I will probably not have time to get through that part in the tutorial where we build a neural network just with NumPy. But from that, actually, that bonus part is actually very illuminating. If you want to know what's going on, what do we mean by collecting things, you can write down your own neural network packages without using PyTorch, and you just put all this as a list and try to know how you would collect things as you go. In practice, no one do that. But if you want to understand all these concept, what do we mean by collecting the gradient, those bonus part will be quite helpful. But more importantly, backprop serve another very interesting operation. Turns out the backprop is much more efficient than forward propagation. Why? Because you're always optimizing with respect to your loss function. And your loss function, by definition, is a scalar. So what this means is that if you look at DLDH, the first dimension is always 1 because you are outputting one scalar. Your H can be some number of hidden neuron. It can be K, but you know that this matrix is always 1 times K. The second one is can be K times K, but still you are multiplying a rectangular matrices with a row columns. And this operation is very cheap because you only have 1 columns. And then once you have done that, as I propagate, I still have an output of 1 times K. So after I've done this operation, it's still a 1 times K column matrix. When I go back again, I'm again doing a rectangular like matrix multiplied by a column like matrix. So this operation is very cheap. But if you do that the other way around, let's just look at the first block. Most of them can be a rectangular like matrix. Then you are doomed, because this matrix itself, this one operation is much more expensive than all the operation that you have done here, because you are doing a very large matrices times a very large matrices. In practice, you do not need to care about this, right? So, but it's important also to just say, why do we call backlog propagation? It serves as a purposes, as a dynamic programming to make the gradient calculation very like effective, and therefore you can take like many steps at a finite computational time. Yeah, so I like this SKCD like a lot. So why do we have the auto like differentiation but not like auto integration? Because like differentiation is just a chain rule. Is it done? No. Like redo that chain rule. Is it done? No. Like do this. For integration, like there's no rules, right? Like you just say, oh, the Cauchy formula, the partial differential, like call your mathematics friends, all this thing, and then you just lost. So the differentiation is just a simple stuff where you just need to know like chain rule and product rule and just do that step by step. And all this chain rule will lead to a bunch of matrix multiplication. And guess what is good at that? GPU. So turns out that neural network, there are different reasons why it become popular. One of that is really it won what we call the hardware lottery. There's no reason why human need to develop like GPU, like beside all the youngsters love to play games. And you know what games is important, because when you output your RGB color on your TV, you need to do a lot of matrix calculation in parallel. So you got to develop. And somehow this is the thing that we need for backlog propagation. And this is the thing that is needed for the neural network. And it wins the lottery. So you can formulate this as cheap gradient principle by just what we have stated, meaning that the back propagation itself to get the gradient is not much more expensive than the forward passing. Why? Because it really comes down to the fact that your loss function is a scalar, and therefore you always have this 1 over k like matrices. So when you backprop, it's kind of the same as the complexity is about the same as evaluating the function. So it's only a few factors of the gradients, and combine that with GPU, this become very popular because you can optimize this very, very quickly. So that's all of what you need to know for 101. And the rest is just for your general knowledge. I think it's good to know. First of all, we just say that you can do the gradient descent. It does not mean that like you will find a solution, right? If you ask in 1990s, like beside Young LeCun and like few people, then no one that believe that like you will find a solution. For 3 reasons, right? So one is, why is it not a polynomial? Like if I fit a billion order like polynomial, why am I not overfitting? Right. So that turned out to be one problem that people thought is just like a flexible function. Turns out that it's not. And this leads to this study of what we call the deep double descent. I will show you what that is. And all these are pretty nice blog posts. These are all very simple like blog posts for the public, so you can understand that. And the other is that even this is not a polynomial, you do not overfit. But then if you use so many parameters, what is the chances that it looks like this, like smooth, right? You can just find a solution, not like, all right. So if you have like lots of parameters, I would expect as a function of the WU, my loss function should be very like jagged, right? Like the avatar landscape, instead of like a nice, smooth like landscape. Turn out that this is another magic. I don't think that people know that until like neural network works and people backtrace and say, oh, after all, we know that. it should be that way. So it turns out that there's something called the neural tangent kernel, which show that in fact, the landscape of the loss with respect to the WU has always been really smooth. So you can start with any optimization. the solution that you roll down is not half bad. In fact, most of the time it's pretty good. And so what the neural tangent kernel say is that no matter where you start with, you will roll to some, say you start here, you roll into some local minimum, but there is a valley and real path that will slowly lead you to the global minimum. And that is another magic that leads to a lot of interesting mathematical study. And this is another of my gripes, right? So a lot of astronomy people say neural network is just a black box, it just has a flexible function, lookup table. Yeah, stop speaking if you do not know what is machine learning. I think that's the reason that why mathematics, the mathematician and statistician are so excited about machine learning, not because it works, but rather there are lots of new phenomenology that we simply did not know. But because it works now, we need to mathematically understand that. The way that I look at this is very like statistical mechanics. You would imagine that it's impossible to understand all the particles in a room because you cannot explain that by classical mechanics. Individual interaction is very, very weak. It's a collective motions. But the neural network turn out to have a lot of global properties of solution, just like all the particles in the room will naturally lead into some very nice form of Boltzmann distribution. That is also happening deep down in the neural network, where people are very excited about. Right? So deep double descent come out in around 2016 or 17, and neural kernel become popular in 2018 and 2019. Grokking is another thing that become really popular since last year, 2022. So let's talk about what is the deep double descent. This is a very nice blog post from OpenAI. So if you look at x-axis as the complexity of the model, think about polynomial. So this will be the degree of polynomial. And the y-axis here is the loss. You would expect in the classical machine learning, as you increase the number of order in the polynomial, you will tend to fit better and better until you overfit. Then you get bad, right? And a neural network just have these nice properties that yes, you will go down at some point, start to overfit, but then at some point, you start to not overfit again. So you can easily fit millions of data with 100 billions of parameters. In fact, it's encouraged to do that. If you have computational power to do that, you should always increase the parameters to some extent. There are still a lot of this blog post. I tell you lots of little thing, but the point is that it's not a polynomial. It's not a flexible function. It just have this amazing the properties that it generalizes the more you parameterize. Good for us, meaning that you don't need to think about what is the optimal parameter that you should use. As long as you have GPU, just go crazy. Most of the time it works, right? So as long as you can do the gradient descent. Since last year, there's something very exciting called grokking. So grokking is if I use 100 billion parameters to fit a million data point. So just like in PCA, if I have 100 degrees of freedom, why can't I just memorize everything? I can, right? So if I have more parameters than number of data, I should, in principle, neuron 1, remember data set 1. Neuron 2, you memorize the data set 2, right? In principle, the neural network can do that when you over parameterize. So people have been debating if the double descent is just a mirage. After all, you are memorizing everything. Just like ChatGPT is not really understand what you say. It just memorizes all the sentences on the internet. Turns out that it's not. And this is the amazing thing. And people can show this. What we call so this is another really nice blog post. Of course, people cannot do things in very high complexity sentences, but people can do simple thing like arithmetics. So a lot of these things are done in simple operation, like if I do A plus B mod C. So if I really understand the concept of A plus B mod C, then I should see a periodic pattern in a neuron, because mod C like ultimately it's a periodic like operation. And you can ask the question, if I feed you fewer data than your neuron, in principle, you can just memorize individual data point. Does the neural network do that? The answer is no. That's also another less surprising thing. Why it does not do that? People start to have like, there are quite a few people in comp science here that are working on like grokking. This is also a topic that I am like quite excited about. So if you're interested in this more, let me know. But this is sort of the general thing that you should keep in mind. A is not like memorizing. It's really like generalizing. And grokking just like, you think really hard and then you reach like nirvana. Right? It's just like go like really so hard and then it's like, okay, like understand like everything is like, I don't know, like Kung Fu soccer or something, right? So you just like go really hard on that. And this sounds to be true. I think like no one can explicitly show that until like 2022, and people start to see all this like phenomenon. And these are why deep learning is very exciting. I think like people always overhype about like DALL-E 2 or like ChatGPT because they are very popular. But ultimately, what is very exciting about deep learning is that you have a lot of statistical behavior of the neuron that we simply like did not know. And then now we found them, then we can understand them. Okay, so why should you understand the theory? This is another joke, which is highly not true, right? So people say, the machine learning is just like you have a bunch of data, you stir the pile, like if it does not work, stir that again until it works. Not really. I mean, practically, like some people do that, but that's not what is exciting about like neural network. But even for more practical standpoint, understanding the theory is important because there is a real consequences of how well you can train your network based on how much you can understand the theory. So in the tutorial, we actually have an example like why people like do not use sigmoid function as the activation function now. So we say that we can choose some nonlinear function. A simple one is to use a sigmoid function. You have learned in the logistic regression that the differentiation of sigmoid is a sigma times 1 minus sigma, meaning that you have two sigmoid and then multiply them. So if you like multiply S shape with an inverted like S shape, then you lead to this shape. And this is a very bad shape because this is like really not decisive. So your gradient is either you can go like really small, but if you still like say, oh, you should go there, it's like overly polite, like until that people like do not know what you mean. You just like keep being too subtle. Sometimes it's good to be like decisive, go, not go. Right? And sigma has this function that after it's like, oh, maybe let's go, and maybe you try, and then maybe you can try, and then like you just get like forever to train. So like sigma is not a very good activation function, right? So anyway, so what we have learned in the theory part, so we talk about neural network as the adaptive like basis function. It really comes from the fact that linear like regression is too like restrictive and therefore it's not a good solution. And neural network is good, and we talk about some of the concepts that we have learned in the linear regression get ported to like neural network, like regularization or weight like decay. You can train a network just by like gradient descent, like what we would do. The magic is like why it works. I think we have some understanding, but it's like beyond the courses here. We talk about the auto like differentiation and back propagation. I think that is sort of the gist of what I hope that you have learned from this lecture beyond a normal podcast, because there are wide reasons we do like backlog propagation, and it's just computationally more effective. And these are all under the hood about like packages like PyTorch or TensorFlow. They are all auto-diff like packages. JAX itself is also a auto-diff like packages. So with this in mind, I will first ask if you have any question, and then we can go to the tutorial part. Question, yep.
Other differentiation in packages only works for predefined packages. Predefined random constant.
Right. So the question is like if I predefine, if I understand correctly, your question is like, if I predefine my activation function, then the auto-diff might not work because it's not a primitive operation.
And predefine that user set if you want to define
Yeah.
your own
Right.
random activation.
Yeah. Yeah. So the question is like, if I predefine my activation function that is somewhat non-trivial, would the package work? Actually, it still works because your somewhat complex function is still made up of like simpler function. So you can just think about what you call g of x is really just written as a bunch of like composite of f. So there is still a more primitive forms. So in the computational graph, there is still a more primitive like version of your operation. So it will still work, right? So anything that you can write down, like literally like anything that you can write down as a coding, it can be like auto differentiable by definition, because whatever we can write down is a primitive. It can be decomposed into the primitive operation. Somewhat tautology, because what is operation if you cannot like define that, right? So at some point you will be breaks down into primitive like operation. Right? It's like, what is human if not made up of cells, right? So it's like at some point you will break out into the most like basic form. Question? Yeah, seems like I spent too much time like driving today. It's slower than what I thought, so might not be able to go to as much tutorial as I want to. So instead of that, I will first give you an overview of so there are different ways to do the auto differentiation, right? So if you follow the logic, the only thing that you want to avoid like writing down is the auto like differentiation, which you can just from the NumPy point of view, which is the bonus part here. So the bonus part here is really writing down a neural network without using any like packages like beyond like NumPy, right? So let me show you this part first, like the bonus part. So like implementing differentiation and propagation with only NumPy. Essentially what you are seeing here is that each time I will define a bunch of properties in the classes, and I will also have the the gradient. And then for individual this like primitive like operation, first I need to know how to do the forward pass. When I pass through a value, how does it pass the next to the next value? But I also do the backward pass, meaning that when I collect the gradient, what operation should I do? So that's sort of the analytic like operation of the gradients for this primitive like operation. And then whenever you have a note that you have something that you can update, you will always like, update that as you do the backward passing. So one thing that we didn't mention just now is, of course, your parameter like do not need to be at the leaf nodes. Your parameters can happen at anywhere in the nodes. Just that if I want to update, say, y, so let's say y is some things that I can update. So I will just do dl dy. So whenever I do the backward propagation, at some point I will reach dl dy. So at that point, I can already update the parameters y, even it's not the leaf nodes. So at any point, at any nodes, you can update your parameters if there is a parameters to be updated. So for any operation, as long as you break them down into the computational graph, it's always forward passing, calculated the intermediate value, backward like passing. And when you hit something, you will decide how to do the forward pass, the backward pass, and if there's something to be updated. And you can define all the classes in the same way. So for individual sigmoid function, you have the forward pass, which is just like passing sigmoid. The backward pass is just sigmoid times one minus sigmoid, but also collecting the gradient that was being passed to it, because you're collecting what is like being passed through that nodes. Of course, for sigmoid nodes, like there's nothing to update because it's not a free parameters. So for any MSE laws, they all have like just need to write down the forward pass, the backward pass, and the updates, right? So when you build a network, it becomes just a sequence of function. So when you do the forward passing, you are iteratively going through the sequence and go from X, update 1, and then pass through the sequences like step by step. So when you do the backward like passing, you are collecting the gradient step by step, right? Like iteratively. So these are the two parts that is important to understand what is like going on in the forward passing and the backward passing. It's really a sequence of function. And each time you need to do two things. You need to do the forward passing and backward passing, but because you have backward passing, each node have two properties. You have the value itself and the gradients of the values. So all these deep learning packages are kind of doing two things. One is to write all these like classes for you so that you can call that with one function without writing the whole class, and it's more optimized. And B is also extending, we call tensor. It's just like you have a NumPy array, but now it's like the double of the NumPy array. So each time I have a property, which is my values, but also the gradient evaluated for these parameters, right? This is a bit hard to explain in words. I think like this is something that if you go through this like bonus part, then you get a better understanding. But I don't think it's that critical. It's just like if you are very confused about all this like forward passing and backward passing, this is a very good way to understand this. I should say that I have not like appreciate this very deeply until I have to like force myself to write through all these like NumPys, and I start to have a good understanding of what is like going on in PyTorch. Okay, so back to what you need. So in most of the cases in machine learning, you will use some like packages. There are few things. One is PyTorch, TensorFlow, and JAX. First, don't use a TensorFlow. That's my very strong opinion. So PyTorch is like maintained by Meta. I think like TensorFlow by Google, and TensorFlow is really not that popular now because like Google spend more time on JAX. So there are three packages: PyTorch, TensorFlow, and JAX. You can think about like PyTorch is the one that is easiest to use as a beginner. JAX is more optimizable in the sense that if you want to train on 100 nodes over like 800 on a GPU, then JAX become quite good at doing the MPI part, like distributing your training. But for most cases, like I think a PyTorch is easier to use. TensorFlow used to be much harder, but then they have like TensorFlow 2, which is fine if you are good at like TensorFlow, you can keep doing that. I will kind of look down at you, but you can keep doing that. But PyTorch, I think I would recommend as a first comer. I think it's quite low bar, as we will see. Okay, so what is PyTorch? First of all, we have learned in the first lecture about how you can get a GPU. So that's just using Google Colab. So if you have no GPU, for most of the things that we'll go through today do not require a GPU. But if you want to train something faster, then you can use a GPU, and Google give out free a GPU. So you can have some new notebooks. You can also subscribe, just like pay for YouTube, then you have a slightly better like GPU. So as I mentioned, like you can either like subscribe to YouTube or Google Colabs, but I think it's the same amount, like $12 US. Make more sense to like subscribe to Google Colabs and just watch like ad. But no, actually like you can, okay, you cannot watch ad on YouTube even you're not subscribed. So okay, so notebooks here. If you want to get a GPU, because by default it's just run on a CPU, so I can just say, I want to have a GPU. If I ask for A100, like it might not give me. I think if I have not subscribed, they ask for a T4 like GPU, then you just become a Jupyter notebook with a GPU. So for not only for like these courses, but for very basic like research, in most cases in astronomy, I don't think you need to go all the way to have your own high power GPU. Even V100 can do a bunch of stuff. There's very rare cases that you need to go beyond that. So that's one way to get the GPU, and then you have the Jupyter notebooks. But because most of the things that we talk about would not require GPU, so we just use the Visual Code Studio. PyTorch is basically like NumPy. So you can start with some NumPy like array, and then convert that into the tensor. And then you can also specify if you want the gradient or not. So remember, like what it's really doing here is doing two things. One is if you're using a GPU, then it will port the NumPy onto the GPU. And if you say, at some point I might need to get the gradient, it will double the storage. One is store the values, the other is store the gradient. And the other operation is it's meant to be very easy to use. So you just change all NumPy to torch. So this is like creating the random numbers. This is like creating ones, zeros, creating a range. And then the rest is the same. You can do a reshaping. You can do concatenation, sum, mean, taking the norms. These are quite straightforward, exactly like a NumPy. We'll show you some example why this is still quite powerful, like using the PyTorch. The other is just one little thing. Because most of the GPU are by default working on float 32 for good reasons, because like GPU RAM is the most important real estate. So the more you can store, the more you can build a bigger models, because the GPU is a part that you might need to upload and download. Upload the data to GPU, and if you exhausted the RAM on GPU, you might need to offload your data. So you want to make sure that if you do not need float 64, then you might want to run on float 32. So the default is run on float 32. In many practices, you can even go less precise things. You can run on float 16 or whatever to really minimizes the real estate on the GPU. So people who have run anything on machine learning, you know that it's kind of just GPU RAM management, 50% of the jobs, just to make sure that how you can efficiently minimizes the number of times that you upload the data to GPU and offload. Now I know she is smiling now. It's half of the job, right? If you know how to minimize that, is the thing. The rest is the same. I will show you one example. So let's start with let me start with gradient descent. Okay. So let's say import NumPy SNP. Do this. Import torch. So let's say I want to do a simple find the minimum of x squared using NumPy. So if I have a function, it's called x squared, I want to find the minimum point, then I can do a gradient descent, right? So what I would do is define the function. Too smart. No, that's not what I want. So we define a function. Also not what I want. I'll start with some initial point. So how do you do the gradient descent in a NumPy? So what I would do is to say I have some number of iteration, the gradient descent. Right. So what I would do is the following. I will start with some x naught. And each time I will calculate the gradient of fx, which is 2x here. And then I will use some step size, as we have seen in the logistic regression, doing the gradient descent part to find the minimum point. Right. So if I do this, then you will see you will start with 6, right? And then it will slowly roll down to 0, because the minimum point of x squared is 0, right? So this is the one that we show here, which is right? So you have a function x squared, and then you start with somewhere, take the gradient, and you just take the step size and roll down to that. One thing here is this is a very simple case, but you need to define the gradient yourself. You need to know the derivative of x squared is 2x. For PyTorch, you do not need to do that, because you can do auto differentiation to find the gradient for you. All right, so do that with PyTorch. This is actually a mistake that happens. So actually I need to be an array, and then the learning rate. So it's more or less like the same. The gradient descent. Oh, this is too dumb. Not one. Okay, so using x naught dot grad. Yeah, so there's something here. I think, yeah, first I need to evaluate y using x naught. Like I will evaluate the function and then do a back propagation. So this back propagation will say, given that x naught is passed to y, when I do y back to x naught, my x naught will have a new value that is stored in an attribute called gradient, which is 2x naught here. And then the last part is saying, because like this gradient by default in PyTorch, like it will try to accumulate. Meaning that if each time I run, like it might not replace the gradient. Instead of it will just accumulate. This is good for some of the neural network application. But for this case, we want to make sure that each time I am just taking x naught, evaluating y, take the gradient at this particular instant of x naught. So if I print that, it will show you the value again from like 6 roll down to 0. The only differences here is that I do not need to know the differentiation of x squared is 2x. So I just need to do the forward passing, and then the backward pass will give me the gradient. But this can, of course, get into very, very complex function, right? So I can easily write down something here that is much more complex. Right, so I will let's say define a disgustingly complex function f, right? Let's see what it comes out with. Too simple, right? I can do anything. I can do like tanh, right? I think I need to do torch.tanh. Not sure it takes tanh. So if you forgot about what is the differentiation of tanh, still works, right? So you would just do the gradient. It's not even updating. So maybe 6 is some weird function. Anyway, so you can write any function that's really weird, but it will calculate the gradient of this thing for you. How do they do that? They break it down into the primitive operation, right? And then try to calculate. Actually, it's more complex because if you write this thing down, this function itself is not a primitive operation. So each time it's building a computation graph that do x squared, doing x cubed, have this graph that combine together, take the tanh. So when you do the back prop, it starts to go back node by nodes to calculate the gradients, right? So of course you can do something more complex. So you can say, do linear regression with PyTorch, right? So let's say I have mixed linear models. Not do this. Let's make some data, make some data, make labels. You want to add noise. Let's not add noise. Let's without noise. Plot data. So I have this data y equals to ax plus b. This would not work because these are both tensor. So in tensor, you want to convert that to NumPy because else the matplotlib will be quite confused because you have double the array. You have the value and also the gradient. You become quite confused. So you will get the NumPy version. So this is your data. Now fit with PyTorch, right? So here I will do is define the function fx. Oh, why this strange? Yeah, let's try ax plus b. Here I will initialize some parameters. I do not know what is a and b. I will initialize that, do some learning rate, number of iterations, do the gradient descent, the same thing, right? So I will calculate. This is, I doubt it will work. Actually, this should be because you usually able to do a gradient when this is a NumPy array, and this is doing that is just a torch like scalar. You need to be a torch array. I'm pretty sure this will not work. Oh, it works. Very strange. Okay, actually, even for scalar, it works for this case. So what is a true value? Like remember, the true value here is 3 and 2. So each time I am calculating the output of y hat, I will calculate the loss. When I do loss dot back, it will start from the output nodes, pass all the way to calculate all the gradient. In particular, I have the gradient for A and the gradient for B. Update that gradient, zero this out, and then I'll like redo this, right? So at some point it will converge to 3 and 2. So this becomes meaning that for any complex function, you can do that with the same lines of code. So this is like fitting a linear regression. So let's do something non-trivial, right? So make some disgustingly complex data. Sort the data. So somewhat more complex, fit that with 2-layer MLP. So remember, right, if I want to write down some function, so let's say I use like sigmoid, right? So what is this? This is a 2-layer like MLP. I have X, do the matrix multiplication, plus that, do a matrix multiplication, plus that. So I am stringing up simple function to make somewhat more complex function. This is very simple because X is one-dimensional, right? But still, you can see that I can write down a very primitive form of 1 neuron 2-layer like MLP. Will be this one. And the thing is exactly the same. Oh, interesting. You think this is a 10-dimensional object? No, I think this is very strange because this is a 1-dimensional data. I don't think this is 10-dimensional. I think this is wrong. Pretty sure it's wrong. Oh, no, this is correct. This is correct. You can do that. So the intermediate steps, you can output any neuron. Like remember here we're just saying that the input and the output, you remember this graph? So for the data set that we have the input and output to be one variable, but there's no stopping of us to use a hidden layer with 10-dimensional. So I will use a 10 sigmoid function to sum that up. So what it really does here is to say I will put X, make that into 10-dimensional neuron, sum that up to get one scalar. And the rest is the same. You can see I'm just like defining a bunch of like parameters. I define some learning rate, number of iteration, gradient descent. This is too simple. Like Copilot should know that, back office. Exactly the same thing. I will evaluate the output Y. I will evaluate the loss. As I do loss dot back propagation, I am doing the calculation here that calculate all the gradient from the loss to all the nodes. So for individual nodes, I know how to update. Based on the gradient, this is just calculating DL-DW1. This is DL-DB1, DL-DW2, DL-DB2. And then I can just do the calculation and then print losses. No, I want to print the result. Okay, let me do that. And then the losses is decreasing, good. Not converging though, so I can go better, I guess. 100 iteration. If I 0 print loss, let's start to get stable. Let's go longer. You can go like longer. Right, good, right? So now with this loss, so I have a bunch of new W1 and B1 and W2 and B2 make a prediction. So I will make some new test case, like in lean space. I will do the calculation with my best the W1 and B1 because it always get overwritten. Now I will just plot the data and plot the best first, right? So it fit really well. Even though I'm not like fitting exactly the formula that I make the data, which is disgustingly complex, not this case, but rather here I'm just saying that this function can be approximated by this somewhat weird 2-layer neural network. But just like any parametric form, I can always update my weights and biases as long as I know how to calculate the gradient. But luckily for us, we do not even need to calculate the gradient because like human is just like becoming dumber and dumber. We have all the packages, right? So you're just like, hey, we will forward pass. You just literally like need to define how to do the forward passing. And then you just do one line log dot backward, you calculate all the gradient, you update as you would, right? In fact, you can be even like better because you can use packages, right? You use Optim and models, or you can even be like be even more lazy. So Optims and model class in PyTorch. So they can become even like shorter. Define models, the MLP model. So here I'm defining some models. So here I'm saying that I want to have 2-layer like MLP from one variable, pass that to 10 variables, then 10 variables back to 1 variables. In between, I will take the sigmoid function. And then the rest is the same. I will initialize the models, like initialize the loss function, define the optimizer, define the iterations. Right. So this is exactly what we have done. But here, instead of defining exactly the output like W1 and W2, even I wrap that into a classes. When I call the models of X, I already make 2 layers like MLP connected with a sigmoid function. So this is calculating the forward pass. But the forward pass has not end because I need to pass that to the loss function. Even loss function, I am too lazy to write down y minus the model square. So I will just use the MSE class. As I do log dot backward, it calculates with respect to all the parameters, exactly this one, right? So I calculate the gradient of like W1, B1, W2, B2. And then I will just say optimizer, even optimizer, I'm too lazy to write down like W1 minus like learning rate, just too lazy. Write down step, meaning that I will do exactly the W1 equals to W1 minus eta times like W1 dot grad, 0 grad out, pass the loss. Human are too lazy now. Okay, make prediction, right? So the same thing. Now I have this one. Now I can just pass through this model class, plot the data, plot the prediction, right? So these are a one-dimensional neural network. You can so we have 5 minutes. I want to go through the second notebook to talk about what that is. So MLP here. So this is just showing that first part we just do the linear regression, some noisy data. Even without like taking the neural network, PyTorch is just a very powerful optimization. So in many cases, it's very hard to write down a very compact like SciPy function because you want to build a model like bit by bits. But PyTorch is very good at that. So you can think about this as an optimization like function, right? So first part we just like fit a line, which is what we have done. And then you can expand this into multivariate linear regression. So WX plus B is also the same few lines of codes, right? And then what we have done in the two example, which is why I want to mention this, because here is the 6D phase space of stuff from Gaia. So you can look at the LBP, the proper motion, parallax, and RV. Because we know that the stars are not just randomly moving, it's moving according to the potential. So you know that in principle, if I just have all this like motion, then I should be able to predict the RV, even I am not like measuring the RV. It's just saying that if I know a star that is moving in a certain direction, I can forecast what is the missing direction. If you use a linear regression, then it would not work too well. So I'm finding a mapping between 5-dimensional to RV. This can be a very complex function that is arbitrarily, there shouldn't be any analytic form. If you use a linear regression, like will not do a very good job. But if you use a neural network, it would do a very good job, right? So you can predict the RV just based on the 5D, which is at one point, like, people think this is a big deal. Actually, there is a paper out there that's showing that, oh, no, you shouldn't do like spectroscopic survey because now we can get the RV just from the Gaia 5D. Completely wrong. So I think that this is the little thing that I need to be like cautioning in the first minute. So all these are finding a mapping between X to Y, but why you can do the mapping between X to Y is making some assumption on the underlying like models. So for example, here, you are essentially saying that assuming the Milky Way is in some hydrostatic like equilibrium, right? What is the most likely RV given I do not like measure that? But those things, this inference itself is completely useless because if you want to find interesting objects, say streams of stars, those things by definition have a different RV from your background. So here you are feeding the background and say, if I have not measured like certain properties, what is the most likely thing? Or even more specifically speaking, you are assuming that the data itself is IID, is independent, like identical and independent, like distributed. But things for like streams of star, those things are not independent, and those makes things interesting. So like when the neural network become popular, you will see a lot of paper. Even today, there are lots of saying that we have trained a neural network that map X to Y. So we write a paper. Be very cautious because that is like really finding the correlation between the data. A, it does not tell you about the causality. And B, you're also making the assumption that you're feeding the background like models. And sometimes it's not the background that is useful, right? Think about open cluster. Those things are exactly because they're clustering together, not following the background. And similarly, people also make a big deal that you should not like run like Galah. Why? Because I can easily infer all the abundances only from two elements. In fact, you can. If you run this like 5 lines of like neural network, I can predict my oxygen down to 0.01 dex. Right? I can predict all these things to 0.02, 0.03 dex. It's somewhat the precision of Galah. And at some point, people always make a big deal. It's like, oh, we are done. We just need to collect low resolution spectra and just measure these two elements, and then we will just infer all the abundances. But exactly the analog, like the data, like the stream of star, because here you are feeding the mean trend, but always in astronomy, it's not the mean trend that we want. If we know that the Milky Way is in equilibrium, yes, right, you have a model saying that there is 5 degrees of freedom of the motion of star, not six dimensional. But all these streams of star or open cluster or correlation of the abundances is because they do not follow the background like model. It's always a background like model that we try to subtract and then find the exciting things, the fluctuation on top of that. I think this is a mistake that get projected quite a little bit about making inference with the neural network is the same as like causality, and all these things are not true. If you are wanting to know what that is, what do I mean? Like there is a paper that I wrote last year, just to, in hindsight, it's not a very tough idea, but just want to make it clear that you shouldn't say I can infer X to Y, then I shouldn't like measure Y. I think that's all the little thing that people tend to make mistake. Okay, question. Cool. Okay, if not, see you next Tuesday. Also, next Thursday, there's no lecture. It's on Wednesday, 2 p.m. here. Okay. And good luck with your assignment. Yay.